another method for synthesizing alkynes that I did not mention in the previous video because I didn't want it to be too long is to add the halogen to alkene, so addition of halogen to alkene, and then double elimination. Like what? Like, let's say you have this alkene and you want to make this alkyne out of it, right? You want to change the double bond to triple bond. So what you do is you add bromine. So you're adding, you remember addition of bromine was anti. So each of these carbons has hydrogens, right? And then you just learned what was the best base, or what are the best bases to do that. You use 2 NH2 negative, so you will end up having, or if you want to do it step by step, let's just do this step by step. You will have, let's say you eliminate hydrogen. So you will end up having this bromine and this hydrogen, and then with another NH2 you will you can draw the mechanism yourself. So that's another way of synthesizing alkynes. Okay. Let's work on the reactions of alkynes. The reactions of alkynes, we study 4 of them. We study addition of HX, hydrogen halide. We study addition of halogen, and we study addition of water, addition of H2O. So in 2 ways, 2 methods. Remember, you had the 2 methods for adding water to alkenes. One of them is called Mercury-catalyzed. Mercury-catalyzed. Very similar to oxymercuration. And the second one is called hydroboration. Alright? So, before we start, for the addition of HX and X2, if you remember, we just needed 1 mole of each to react to add them to double bond for alkenes. But for alkynes, we need 2 moles of each. We are not going to work on their mechanisms because you already know the mechanisms from alkenes chapter. And these 2, we just need to learn their products. These 2, the addition of water is what is going to be a little bit different, and it's going to make a difference in their products. So, addition of HX. You remember, or let's say if you have an alkyne and you add HX in ether, we go with the same rules of Markov-Nikov. If there is any difference between the carbons as far as the number of hydrogens, it still follows the Markov-Nikov rule. and it will form an alkene, just 1 mole, right? 1 mole is enough to change alkyne to an alkene. Then, if you use another hydrogen halide, another Markov-Nikov reaction will happen. Now there is a difference. So hydrogen will stick to this carbon with more hydrogen and halogen to this carbon. So you will end up having dihalide. So for alkenes, you just need 1 hydrogen halide. In order to fully saturate the triple bond, you need 2 moles or 2 equivalents of HX. If you see 2 moles or the word equivalence means 2 moles, so means to have enough to saturate the triple bond fully to a single bond. The same thing for halogen. So with their chlorine or bromine, which are the most famous in CH2Cl2. Here, Markov-Nikov doesn't matter because you're adding 2 identical atoms. But you only need to keep in mind that the addition is anti-addition. So you will have X here. The other X on the other carbon must be on the opposite side, and R. And then the second halogen molecule comes to fully saturate triple bond. Here you end up having a tetrahalide molecule. That's the difference between alkenes and alkynes. Means that alkynes need more, we call these reagents, more reagents to react. Whatever you write on the arrows, the compounds that react with your reactants are called reagents. So for alkynes, you need more reagents comparing to alkenes. So, for example, if you add this, first of all, how many carbons do you have? We said when you see the triple bond means 1, 2, 3, 4, 5, and 6. Okay? So when you add, we're supposed to draw the products for 2 equivalents of HBr. 2 equivalents of HBr. Feel free to draw the first one with 1 HBr first, especially at the beginning when you are working on the reaction. So this one has 1 invisible hydrogen, right? So this is the hydrogen-rich carbon. It's a Markov-Nikov reaction. Please review and repeat and write these facts about every single reaction the way I do for you and for myself, to remind myself about the facts about every reaction. So first you have a CH2. I don't have to write it, I just want to show you. And then you have a bromine here, right? 3, 4, 5, and 6. 1, 2, even if you don't write this, means this is the first carbon. 1, 2, 3, 4, 5, 6. Now the second HBr. This is the hydrogen-rich carbon, so we will have 1, 2, 3, 4, 5, and 6. So we have 2 bromine on the same carbon. Okay? I will work on the second one because there's a point in the second one, on B, that I want you to know. Okay. Now, with 2 HBr, let's react with the first HBr. This is the first first carbon, this is the second carbon. Is there any difference between the carbons of triple bond as far as the hydrogens? No. So we can have let's write them as, how many carbons do you have? 3. 1, 2, 3. You have a double bond here. Oops, a double bond here. So means bromine can attach to here, hydrogen to here, or vice versa, right? There is no difference between the carbons as far as the number of hydrogens, so Markov-Nikov rule can apply to any of these carbons, hydrogen, bromine, right? And then with the second HBr, again another Markov-Nikov, but now it matters. Now this is your hydrogen rich, but this is your hydrogen rich carbon. So you will end up having 2 products. You see? Definitely can name them different. So when there is no difference between the carbons of triple bond, you will end up having 2 types of products, as long as you can name them. And then the next practice is just testing you for understanding the name of the amount of the reagents. Sorry, no name here. So if you have first 2 equivalents of bromine or 1 equivalent of chlorine. 2 means you are fully saturating your bonds. So CH3, how many atoms? Means 4 bromines, right? So you have C, fully saturating means there will be no multiple bond. Everything will change to a single bond. Feel free to draw it stepwise. That's what we did so far. But here, 1 equivalent means 2 chlorine atoms, right? 2 chlorine atoms means ending up with an alkene. So CH3, CH2, C, CH2, CH3, and don't forget this addition is an anti-addition. Okay, so that's the difference when you see 1 equivalent or 2 equivalents. That's what it means. All right, the big difference between the reactions of alkenes and alkynes is addition of water to them. I told you there are 2 different types of addition of water. First is Mercury-catalyzed. Mercury-catalyzed, very similar to oxymercuration. Again, you need to use mercury, but the reactants instead of mercury to acetate is mercury to sulfate in water. And HgSO4 on the arrow. Okay, so let's consider we have this alkyne, okay, and we are adding H2SO4 with water. Obviously the acid is your catalyst, but again we are not going to study the mechanism. Good for you, you don't need to know the mechanism. So what happens is that if you remember, oxymercuration was Markov-Nikov, so we still have Markov-Nikov, the same, and if you remember it was anti-addition. So the same facts about oxymercuration is applied to mercury-catalyzed on alkynes. Now, if we say Markov-Nikov means hydrogen will be added here and OH will be added here, right? So we have OH and we have H, right? And and we said it's an anti-addition, so hydrogen and OH are on the opposite sides of each other. Now, the difference is that we call this compound enol. Enol. Why? Because it has the en and it has the ol. It has double bond and it has alcohol. So en is for double bond for the alkene and ol for the alcohol. Seems like when the studies and research were done on these products, nobody got anything with the properties of an alcohol. So it seems like this hydrogen-rich carbon is still hungry for more hydrogens. So it grabs this hydrogen, okay? It grabs its hydrogen, so we have 3 hydrogens, right? If you keep double bond here with 3 hydrogens, because we had 2 hydrogens at the beginning, the 3rd hydrogen, we are violating the octet, right? So double bond disappears here, and this carbon just has oxygen and 3 bonds only. So double bond forms here. So as if like hydrogen shifted on the other carbon and double bond shifted between carbon and oxygen. This is called keto, not ketone. Keto form because it looks like a ketone. So by studying the separated product from this type of compounds, the compound had the ketone properties as far as like both the boiling point, melting point, the reactions. It was more close to the ketone than the alcohol. So that's what happens if you're supposed to determine the final product of a mercury-catalyzed reaction on an alkyne. That's the keto one, not the enol, because enol is very unstable. As soon as it forms, upon its formation, it changes to keto, which is a very stable product. So what happens is that double bond moves between carbon and oxygen. Instead of OH, you have carbon-oxygen double bond. We call it carbonyl. And hydrogen sticks to the hydrogen-rich carbon. That's for mercury-catalyzed, which is Markovnikov and anti-addition. The second one was hydroboration. Again, the same hydroboration process, which is non-Markovnikov and syn addition. So hydroboration. With the BH3 and H2O2. Okay, so we go with the same example of general formula, BH3 and H2O2. I believe there is a base involved, but we keep, we have a base here also. All right, so we have a non-Markovnikov, means hydrogen is added to hydrogen poor carbon, and a syn addition. So you see the significance or importance of knowing the last chapter very well. So the basics is in the last chapter. Learn it well and then move towards this chapter. Alright, so if it's a non-Markovnikov, so hydrogen will be added here and OH will be added here, right? So we will have R, H, it's a double bond, right? So H and OH. It's a syn addition, so you see both of them on the same side. Again, it's an enol because we have alkene and we have the alcohol, so we call it enol. Now, what happens? The same exact story happens. This hydrogen will be rolled towards this carbon, and double bond forms between carbon and oxygen always because we need a keto form. So we will have R, H, and H, and here we have We don't have double bond here anymore because we will be violating the octet on this carbon. Instead, we have this. So we will have a keto. All right? Now, again, this is unstable. And this is stable. So this is the very final product of hydroboration. So the location of carbon-hydrogen double bond shows you what type of water addition, your hydration you have. So let's work on some examples before we move forward. So let's say I want to hydroborate this, do the hydroboration on this one. So we need to find out which one is hydrogen-rich carbon first. This is the hydrogen-rich carbon. It already has one hydrogen, right? So hydroboration is non-Markovnikov. And what's the addition? Syn. So hydrogen will be added here. OH will be added here. So first, at the beginning of learning this, you do it step by step. Don't jump to the keto, and otherwise you will mess it up. So then now you have two carbons, right? And a double bond. So OH adds here, H adds here. But enol changes to keto. What happens is that double bond between carbon and oxygen moves here. So this is what you end up with. And you have a hydrogen here that you don't show, so this is a keto. And the hydrogen moves towards here, so it has two hydrogens. Here, because this is the first practice, I will show the hydrogens here, and because you already have the hydrogen here. So this is the hydrogen that has moved. So that's the only difference between alkynes and alkenes. Move the hydrogen from OH to the other carbon and form a carbonyl bond, carbon-oxygen double bond. Now let's add one pentyne to H2SO4, H2O, and HgSO4. So let's draw pentyne. 1, 2, 3, 4, 5. One pentyne triple bond is on the first carbon. So now we have H2SO4 and water. And we have Mercury-2 sulfate. So we have Mercury-catalyzed. Please write these while you are studying and practicing. This is Markovnikov, and it's an anti-addition. So we have to apply these facts. Markovnikov means this has already one hydrogen. So hydrogen will be added to this carbon. OH will be added to this carbon from opposite positions to show the anti-addition. Okay, so you have a double bond and you have hydrogen here, two hydrogens now, right? This is the hydrogen added, and OH is added here, right? Now hydrogen moves here, double bond moves here. That's the enol. We never have enol as the final product. So the last thing I need to mention is that the process of changing enol to keto is called tautomerization. Tautomerization. And it's essential to know its name. Please don't forget. It tautomerizes to keto from enol. So tautomerization is for changing enol to keto form. So that's about the reactions of alkynes, and not much difference except the hydration, and you are not working on a whole lot of them. So that's all. Let's move towards the next concept, acidity of alkynes.